So at 0 to 0 millimeter. Again, if we can draw it out, then we can visualize better. Okay, so we have x, this is the y-axis. So we've got one charge minus q, and one charge as plus q. And the vector position, this is at -1, this is 1. And we're interested to look at the electric field at the point 0, 2, 0, 0, which means that at the y-axis equals to 2, and x and z is equals to 0. So again, we can write down the vector positions between the charge and the positions of observation. Let's call this R1, this vector R2. So again, we can solve this as two separate problems, and then we sum up the two. Okay, so we can do this. -1 with a charge of minus q, 2 R1. Okay, and our E field we assume to be pointing away. So we can first work out what is R1, our vector R1. So our vector R1 will be this vector plus this vector. So that will be equals to 2, 0. It's 0, 2. 0, which is this vector. And then minus 1, 0, 0. This gives us 1, 2, 0 millimeter. Our unit vector so that will be divided by √5. So we can now calculate the electric field. So we call this E1 equals to Q1, or Q1 as our minus Q, 4 pi epsilon naught R1 squared times the unit vector R1. So Q1 is equals to minus 0.5 times 10 to the minus 12, or pi 8.854 times 10 to the minus 12, root 5 times 10 to the minus 3 squared. We have 120 over root 5. That gives us minus 402, 120 volts per meter. The other one will be 1 plus q with a vector R2 and our electric field E2. And this is at y equals to 2. So again, writing down the vector R2, that will be equals to 0, 2, 0, minus 1, 0, 0. So that is actually this vector plus this vector. This will be minus 1, 2, 0 millimeter. Unit vector R2 minus 1, 2, 0. Again over root 5. The electric field E2 equals to Q2. Would be 0.5 times 10 to the minus 12, 4 pi times 8.854 times 10 to the minus 12 times root 5 times 10 to the minus 3 squared times the unit vector. This is 402 minus 120 volts per meter. Photoelectric field will be the vector sum of E1 plus E2. It will be minus 402 minus 804 0 plus minus 402 This is 8040. So the sum of this will be equal to minus 8040 watts per meter. So what this tells you is that the electric field in this scenario is equals to a vector pointing in the minus x direction. Means that the vector of the total E field in these directions with a magnitude of 804 watts per meter. Okay, so the electric field in the y and in the z directions is equal to 0. So there's no field in the other two directions. So intuitively, I mean, we can look at the diagram that we have there. So we know that this is positive charge. So the electric field is pointing away. So this is now E1. And this is negative charge. We know that the electric field is pointing towards the charge, E2. And they are of the same magnitudes because they are same distance away. And the charge are the same magnitudes. So if you resolve these two vectors, this is our resultant. And the y component, we have one going up and one going down of the same magnitude, and they cancel out. And in this scenario, there is no z component at all. Okay. And that is also the case in our calculation. We show that the y component, we got one going in the negative y directions of 804 and one in the positive y directions, also 804. Therefore, these two fields cancel out.